Say you've got two crowd simulation models, A and B, and you want to know which one can best reproduce a given pedestrian interaction. You can then choose some reference data and simulate it with both models. In this case, model B seems worse, as its trajectories aren't very accurate at the end. However, you could change model B's parameters and thus much improve its trajectories. At this point, it would now seem that model B is the better model. This raises the question, how to compare crowd simulation models in a fair way. To solve this issue, we propose a framework that compares crowd simulation models based on reference data with different metrics. This framework also performs parameter optimization to take into account the model's best level of performance. In this framework, we've implemented several metrics, such as the difference metric, which compares the successive positions of real and simulated pedestrians, the progressive difference metric, which compares the reactions of real and simulated pedestrians to the same situations, here represented by their velocity vectors, the interpedestrian distance metric, which compares the mean distance between pedestrians of real and simulated crowds, as well as metrics based on path length, crossing order, vorticity, and fundamental diagrams. In the framework, we've also implemented a few optimization algorithms. The one we prefer to use is a combination of genetic and greedy algorithms. Here's an example of such an optimization using the difference metric. The second part of the video shows three applications of this framework. The first is about comparing models based on microscopic data with the difference metric as an example. In the second, we match macroscopic features in the form of fundamental diagrams. And the third application shows how we can enforce constraints on agents in an animation-oriented context. First, let's start with microscopic data based on which we calibrate and then compare models, here with a difference metric as an example. Please keep in mind that a lower score indicates that a simulation is closer to the reference data. The first situation is a simple crossing scenario between two pedestrians. With the stock parameters, none of the models can correctly replicate the crossing, and thus the trajectories differ from the real ones. After calibration, however, the synthetic vision-based model on the right is the only one where agents correctly avoid each other. In the second situation, both models lead to the correct trajectories, but with the stock parameters they are not well synchronized with the real pedestrians. After calibration, the tangent-based model on the right has agents that accelerate and decelerate at the right moments, and thus are better synchronized with real pedestrians than the model on the left. The third situation involves 6 pedestrians in a circle engaging in more complex collision avoidance. With stock parameters, the real and simulated trajectories differ significantly, while after calibration the RVO2 model on the right matches the original trajectories better than the model on the left. In this last example, we have two intersecting flows of pedestrians. Note that in this case, pedestrians are constantly appearing and disappearing from the camera's fields of vision. For this reason, we extract a time window during which the positions of a selected subset of pedestrians are always known. It is then this subset of pedestrians that we evaluate. With stock parameters, simulated agents drift away from their real counterparts, which is not the case anymore after calibration. In the second application, we calibrate models to match macroscopic features, in this case fundamental diagrams. Fundamental diagrams are used to monitor the relation between a crowd speed and density. Usually as the density increases, the speed decreases. Here we have represented two fundamental diagrams, showing the cultural differences between German people in red and Indian people in green. We have then matched the RVO2 model to these diagrams. The following video segment shows German and Indian behaviors for a low-density high-speed scenario as well as a high-density low-speed scenario. As you can see on the top two videos, for the same density, agents with an Indian behavior travel slightly faster than their German counterparts on the two bottom videos. In the third and final application, we show how we enforce constraints on agents in an animation-oriented context. In this case, a user starts with a sketch idea of a target behavior. The framework then interprets this as a graph of waypoints and constraints and computes the situation with one set of parameters per constraint corresponding to the wanted behavior. In our first example, we want to control the size of a group of agents. We want them to start out grouped, then disperse, and then regroup. We can do this by using the interpedestrian distance metric. First we set zones with a low distance between agents, then the zone where this distance should be highest, and then the zones which will serve as transitions. Note that the 3D animation on the right was rendered using the Golem Crowd plugin for Maya. In our second example, we want our agents to behave in a vortex-like pattern. To achieve this, we use the vorticity metric. Here the sign of the target value dictates the rotation direction, while its absolute value dictates the size of the vortex's radius. Thus, on the left we have an anti-clockwise large radius vortex, while on the right we have a clockwise smaller radius vortex. In our last example, we have two groups of agents entering through two entrance corridors, which then merge and exit through the last corridor as one group. In this case, we've enforced a low-density, high-speed point of a fundamental diagram on the two left entrance corridors and the right exit corridor, as well as a higher density, lower speed of the fundamental diagram on the two right entrance corridors and the left exit corridor. As a result, we have two sparse groups on the left and two denser groups on the right. After merging, the roles are switched, and the group on the left is dense while the one on the right is sparser.